Hello and welcome back to another episode of Kerbal Space Program with your host, Pedantic Planner. Today we got some cool stuff going on, but to do that cool stuff, we're going to need some science. So this little craft you see right in front of you is basically a science buggy. It's got a thermometer, barometer, mystery goo container, and a material science junior, as well as our fearless scientist. And he's basically going to drive it all the way around the VAB. If you didn't know, on the Kerbal Space Center itself, there are many different biomes, none of which are particularly strong in return scientifically, but getting through all of them with a host of experience should net a pretty good amount of science. To really make any progress beyond the local low orbit of Kerbin, we're going to need that relay network constellation we took a contract for last episode. With the science from the Kerbal Space Center, we pick up a few technologies, some precision propulsion, flight control, advanced flight control, and miniaturization, as well as electrics, which we will need to actually put solar panels on our craft to generate electricity in situ, or in other words, while on mission. Funds are a little tight at the moment, so I cannot afford an upgrade to the VAB and Launchpad. To help with this, we're going to pick up a contract for a low-resolution altimetry scan and multispectral ScanSat survey of Kerbin. And we're going to need to create our relay network satellites now. Creating a relay network that provides stable communications out to a specified radius can be a little involved, but I've got some graphics that will help explain the process. First off, we need to choose what antenna we're going to be using. This is going to dictate the allowable orbital height that we're going to be able to sustain constant communications throughout. I'm going to go with the CD020 as my dish antenna. We're all going to point at whatever active craft we have, and they've got a fairly wide cone, which means they don't have to be aimed exactly at every spacecraft in that cone. As long as the spacecraft is in that cone and the cones overlap, they should be able to communicate. Along with the communicatron for omnidirectional signal, we're going to be able to have a network that should support us to the moons of Kerbin. One of the major issues with designing a satellite, even though we have solar panels, is getting them all to be covered. When you have a satellite that has two antennae like this does, or any sort of electrical drain, keeping that satellite powered is a constant struggle, especially with a lower orbit. As the orbital period drops and you orbit faster around the planet, a higher percentage of your time is spent in shadow, which means that your battery capacity and your generation need to scale up to compensate. Taking a look at the actual values for this planned relay network, I'm using Visual Remote Tech Planner to help me identify what I need in terms of antenna and for generation and capacity storage. In this case, an orbital altitude of 1,000 kilometers will give me a line of sight between each satellite of 2.26 million meters. The communicatron can handle 2.5 million meters, meaning that when the satellites are above the altitude specified, they should still be able to maintain line of sight and thus communications. This should give us a stable communications network out to 2.7 million kilometers from the center of mass of Kerbin, assuming our orbit is equatorial. If it's not, there'll be less range. This website also quite helpfully dictates how much power these antennae will draw when under use, and the amount of dark time you'll have in your orbit. This lets us know the required battery capacity and generation in order to maintain constant power. In our case, we're going to have a nighttime period of 827.9 seconds, which will give us a battery requirement just shy of 580. We also need to be able to generate at least 0.8 or so electrical charge per second when we are in the sun. And given this, we're going to basically have to plaster the entire thing with solar panels to achieve these numbers. A higher orbit would give us less time in the dark. And in real life, or with the mod Principia, you can achieve sun-synchronous orbits, which will, using the bulk of the planet's mass being around the equator, slowly drift your orbit such that at all times your satellite has a sun-facing side. This is not possible with the limited physics simulation of Kerbal Space Program, wherein everything is calculated as a sphere of influence. Lastly, we need to consider how exactly we're going to be getting those satellites up to that specified location and spaced 90 degrees apart in their orbital period. To achieve this, we're going to use a multiple launch technique, wherein the bulk of the craft is launched as a cluster of satellites in a resonant orbit with the target orbit. You can see we have two options here provided by the website, one of which is at a lower orbital period and one of which is at a higher orbital period. These orbits are carefully selected such that when the main craft completes one orbit around either of these synchronous orbits, any satellites in the target orbit will have adjusted themselves 90 degrees forward or backwards of the main body. Another option would be to perform 4 single launches, wherein each satellite is inserted at the target orbit at a time which synchronizes it 90 degrees apart from its peers. This does decrease the amount of complexity required per satellite, as to eject each satellite into its target orbit, it will require some form of maneuver or thrust, but it does, I find, take significantly longer to do this, and it's not as pretty. To reduce the bulk of the transfer stage, I'm going to place all 4 satellites into the lower orbital period, whereupon at apoapsis, one by one they will be detached and accelerated to the target orbit, meaning each satellite will need a minimum of 166.4 meters per second. I like to include margin in this calculation because final trimming of that orbit helps with synchronicity, and that means I'm going to be aiming for about 200 or so meters per second per satellite that's going to be in the stack. What I'm doing here is creating a standard booster, which should be able to push a payload of about 5 tons into a low Kuiper orbit. Once I've created this booster, I won't have to really bother making a separate launch vehicle for every payload within the 2 to 5 ton range, depending on where it's heading. Saving it as a subassembly, I can now attach it to our subassembly satellites. All 4 relay satellites are stacked up and ready to be attached to their booster. And very shortly, we'll be launching these up into their target orbit. This kick stage should be able to handle our next few missions and ultimately save us time on the designing of launch vehicles for quite some time yet. Our VAB and launch pad are not developed enough to handle a rocket with quite as many parts or quite so much mass as this one, so we launch from the runway, which doesn't change too much about the ascent. I'm taking a significantly more shallow ascent profile than the launches from previous video because I don't anticipate too many issues getting this thing into an orbit with the amount of thrust that the second stage has. However, I do briefly go back to the Kerbal Space Center to upgrade my tracking station and allow me to create maneuver nodes, which should help me create my orbits a little more finely. Upon reaching a low circular Kerbin orbit, we create a maneuver node to kick us up to the apoapsis of 1,000,000 meters. The functionality of remote tech is such that there's a flight computer built into every probe, and by using it, you can create a maneuver node and schedule a burn to be completed automatically at a given time. This is quite useful, especially when you have a burn that needs to happen on the far side of a planet for which there is no relay network, and it allows you to plan ahead. Once at our orbital apoapsis, we execute a burn to increase our perigee to that specified resonant orbit, and extend our antenna at this time so we can maintain communication when the Kerbal Space Center is in line of sight. Completing this burn right at our target altitude, we can create a resonant orbit. After waiting a full orbital period so that we have line of sight with the Space Center, we go ahead and inject our first satellite into its target orbit, circular at 1,000,000 meters. The thrust to weight ratio on these individual satellites is not very good, but they don't need to move very far. At apoapsis and periapsis, I continue adjusting the orbit to get it as close as possible to my 1,000,000 meter target. If you were unaware, the function of a period of an orbit is determined entirely by the semi-major axis of that orbit, meaning that getting this period perfectly will help keep the satellites stable. A few orbits later, and we can inject our second satellite into its target orbit. You can see that our first satellite is now 90 degrees lagged behind our second satellite. And all we have to do from here is connect the last 2 satellites into their desired point in the orbit. As I'm getting this constellation set up, you'll see me jumping back and forth between each of the satellites to really make sure that their orbital apoapsis and periapsis are as close to circular as possible at the target altitude. Because we're going to be using no more than maybe a day's worth of actual orbital maneuvering, drift shouldn't be too much of an issue, but the closer it is to perfect, the happier I am. With our third satellite now in its designated position and its orbit trimmed, we can adjust our last satellite. Unfortunately, I did not include any sort of probe in that second stage, so it'll be left as space junk. However, In future missions, I will make sure to include some sort of ability to deorbit any spin stages. After turning on all the antenna, we can make sure that all the dishes are pointed towards whatever active craft is being used, rename them, and watch the constellation settle in. One more mod that's super helpful here is Station Keeper, which allows you to, with RCS or liquid fuel, make corrections within 1% to a given semi-major axis. This just keeps everything lockstep. If you set all the semi-major axes, in this case 1 million meters, the exact same, the satellites will never change their relative orientation to each other in terms of period. With our relay network in place, we can go ahead and create a satellite which will be able to conduct a radar altimetry and multispectral scan. As well as this, we're going to be picking up a contract to return some scientific observations in a probe core from Kerbin orbit successfully. And to accomplish this, I'm going to make a 2-part satellite. One part will stay in orbit and will have the equipment for the scans. The other part will deorbit and contain the valuable and very dataful scientific equipment. Both of them need to be able to independently communicate and maneuver. However, the top stage we will not include any engines on. We'll simply inject it into the desired orbit. However, we will include a docking port. I have plans to come back and take the satellite later in the episode to the moon and perhaps beyond in the future. The structural tanks I'm using have therefore included a little bit of liquid fuel and oxidizer for future use of future missions. Another scientific experiment included in this satellite is a imager, which should allow us to take pictures in space near and high over every biome on Kerbin. It may take a minute, but we're going to be using that science later on in the episode. We'll definitely need it. Furthermore, for a satellite of this nature that needs to see the entire planet, the best option is to inject it into a polar orbit. We're going to be heading towards the north from the Kerbal Space Center, and this will cost a little bit more delta V than is typical for an equatorial orbit. Because the planet is spinning in the direction that we normally launch from, that orbital speed is essentially added to our craft and therefore subtracted from our necessary delta V to reach orbit. However, to enter a polar orbit, we're going to need to counteract that equatorial spin, which actually increases the delta V required. You can see our ascent profile in a northerly direction puts us into a pretty good trajectory to enter our target orbit. And we have to burn sideways a little bit just to cancel out the last amount of rotational speed given to us by the planet. Unmanned missions like this become a lot easier when you don't have to worry about timing your burns such that you have a connection to the Kerbal Space Center. After our final orbital injection, I can tell that we're a little bit off of our desired inclination of 0. So I create a plane change maneuver and spend a little delta V, really making sure that we're facing due north over the poles. If we're too far off to one side or the other, we will miss the very tip of the planet, both north and southern, and therefore be unable to see it with our cameras. The second stage of this rocket, I included this time a probe core, which allows it to deorbit and burn up in the atmosphere. And after a few orbits, we take our readings and detach our lower reentry module, timed such that we'll be able to reenter right over the KSC in the water during the day. After a relatively simple deorbit burn, we can recover this craft and the science, as well as the money completion from the contract. Returning to our surveyor probe up in orbit, we can activate a radar scan via the top antenna and go ahead and pick up all the imaging science that we can from every biome on Kerbin. This is a quite long process, hence the speed of this clip, as I have to wait for the planet to rotate into view over every single biome that it has. Once our radar altimetry scan complete, we can go ahead and collect the data from it and start our multispectral and biome scan. ScanSat is one of my favorite mods of all time, simply because of the absolutely gorgeous and useful maps that it creates when used. We'll be using this probe to scan the moon, specifically biome and altimetry, to help us complete contracts on the next episode. The altimetry map will give us an ability to determine the best, flattest landing spots, and the biome scan will let us know where we need to land in order to collect scientific readings. One tip I use here is to configure my science alert to stop time warp when it has a new experiment to be run, which allows me to more easily complete my contract. We'll take the next contract for the same altimetry scan and biome scan for the moon. However, our current equipment is without a way to move itself. So another contract I pick up is orbital rendezvous. These two can be done at once. I'm going to create something of a little tug ship here, which should be able to go up and dock with our probe in orbit and inject it into a polar moon orbit. When designing the first craft, I left some fuel in as structural tanks. I needed the space, and I figured it might as well be carrying something useful. So when we actually get up there, the satellite in orbit has a bit of fuel left over we could use and transfer into this lower stage to give us just a bit more delta V. I have to make sure to include a long-range antenna on the second stage, as the current equipment does not have one, so we'll be able to communicate with it in orbit of the moon. Our launch profile this time takes us south. Given that the planet has rotated while the orbit itself has not, it now appears to the KSC like the satellite is coming from the north to the south. Getting up just to an orbit barely above our target one, we can establish a chaser orbit. Wherein the lower altitude satellite will have a slightly smaller orbital period, and over successive orbits will appear to catch up with us. Since both satellites are in relatively circular orbit, all we need to do then is time a burn to lower our current perigee to that of the target satellite in such a way that at the time we reach that perigee, it'll be concurrent with the target's position. While complicated in principle, it's actually not that hard to do with the wonderful tools that KSP has for creating and editing maneuver nodes, and in short order, I have a close approach of the satellite. I expend a little bit of delta V to lower our relative velocity, and align myself to the probe using the RCS I included on this upper stage. We're on final docking approach now, and I could have done this with even less delta V by being a little more patient, but I had the delta V to spare. Disaster nearly strikes when I almost forget to extend the antenna on the second stage, and it nearly interferes with our docking. The mod you see on the right hand of the screen is called Docking Port Alignment Indicator, and it's very helpful when trying to make these precise docking attempts. With docking complete, we can now turn our attention to an injection should put us on an encounter with the moon. I time a burn a few orbits from now. That should give us an approach of the moon, and we should be able to enter its sphere of influence. I also picked up earlier the contract for flying by the moon, but when we actually enter the sphere of influence, that contract will complete automatically, meaning that we can then pause, go back to the Mission Control Center, and accept a contract to orbit the moon before actually completing our injection burn into lunar orbit. Going from a polar orbit to a polar orbit of a moon orbiting body is not very efficient, but it's also not a very heavy craft, and we have the delta V. However, if we're looking at my fuel readings right now, you might think we do not. This is because I have yet to transfer the residual fuel from the probe itself into the lower stage. When I do that, you can see we gain quite a significant amount of delta V and are able to complete our burn. This injection burn was not very carefully tuned, so I'll need to execute a plane change maneuver to get us into a true polar orbit of the moon. And here's that residual fuel being transferred into the lower stage. Once in a polar orbit of the moon, the first thing we'll do before actually attempting our radar and altimetry scans is take the opportunity in space high over the moon to collect all the imaging science from those biomes. This also was a quite time-consuming and lengthy process, as the moon does not rotate very quickly in respect to Kerbin. In fact, it is tidally locked, meaning for every rotation of the moon, we needed to wait a full month for the moon itself to do a full orbit around Kerbin. The electrical charge available to this craft is not super high, but the solar panels themselves are able to see enough sunlight to allow us to essentially transmit the readings as we get them. Taking our periapsis down to 70 kilometers, we burn to circular eyes at the best altitude for the altimeter and the multispectral scanner to complete their work most efficiently. This also counts as in space high above the moon. The cutoff for space near the moon is about 30 kilometers, which means that we can conduct both our radar and altimetry scans, multispectral scans, and imaging observations all at once. Annoyingly, sometimes the probe is in darkness for the moon. For the multispectral scan to actually function, we need to have an illuminated surface, meaning that this whole process will take about 2 months of game time. In the tracking station, you can accelerate time warp beyond what is possible in a low orbit of a body, and this allows the scan to take not much real time. You can see our altimetry and biome scans are complete, and when the data is transmitted back. I had some intent of trying to get this probe to come all the way back to Kerbin via aerobraking, but I eventually discarded the idea after messing up a few burns. However, I do inject the probe into a low enough orbit of the moon to count as in space near, which gives me a whole new set of imaging observations to collect and transmit back to the Kerbal Space Center. This is a non-insignificant amount of science that should greatly assist us in future episodes. Next episode, we will be landing on the moon with a rover, and furthermore, attempting to get crewed presence. Getting a human crew to the moon will give us the opportunity to collect much more readings in terms of scientific data and much more science from them, but the complications of getting a living, breathing person all the way out several million meters to another body increases the complexity somewhat. Finishing up the last observations, there's only one biome left, and it's the canyon biome, which is very slim, but I adjust my orbit so that I should arrive right over it at the correct time. Somewhat in error, I attempt to deorbit this satellite to a low Kerbin orbit so that I could perhaps attach a new freshly fueled tug to it, but I find I have not the delta V nor the connection to make this happen. There is some RCS fuel left on the probe, but not enough to effectively deorbit it, especially because I wasted a lot of delta V on attempting to change my orbital plane. However, we made a lot of money by completing all those contracts, and we can afford the loss of this hardware. I get another moon encounter purely by accident, which I use to try to change my plane even more, but it's just not quite enough. However, with that, I think I'm going to end the episode here. I'm trying to keep these shorter as per some feedback I received. Hope you guys learned something about orbital relay networks and how to create them, and get excited for next time when we'll be landing a rover on the surface of the moon. I'm Predictive Planner, and have a good day.